Hey, what's going on, guys? Keyhan Vakil here. In this video I'd like to demonstrate an out of this world x86 assembler written in x86 assembly in under 512 bytes, believe it or not. So here is the project, and just a few words how did I manage to find it actually. So I've created my own 16-bit real mode operating system intended for running and potentially developing boot sector games and apps, and the only development environment I had there so far was and still is the hex editor, so I can just do some hand assembling, then input the machine codes into the hex editor and then run it and enjoy the show, right? And I've made quite a few videos on how I was actually doing that, and the most significant of those is I've coded a matrix screensaver in only 44 bytes. And I did this in machine codes by hand assembling the x86 assembly to machine codes. Now, but that was quite pretty boring to watch, because instead of being focused on the programming itself, on the programming logic, instead the viewer was actually forced to watch my skills of converting hexadecimal numbers to binary back and forth, which is not really that exciting, I believe. And I thought that it could be cool actually to have an assembler, so I would be able to input the code in x86 assembly even with a minimalist instruction set, but still then just run the assembler to come up with the machine codes and then run those machine codes as the executable. That's pretty much all about it, right? But I was thinking that creating an assembler in 512 bytes is literally impossible. Well, at least for me personally, it was so, until I came up with this sort of a project. So this project is called ZeroASM. It's created by Keyhan Vakil, right? And what it is, so this is the 16-bit x86 assembler written in 16-bit x86 assembly, which fits in under 512 bytes of x86 machine codes. And originally it's intended to run with a bootOS. So bootOS is another minimalist operating system. It's written by Oscar Toledo, and it's really cool, and we'll see how it works eventually, because this ZeroASM is not a standalone stuff. So first, we'll make this run. I'm going to be using the online emulator, so you don't even need to install any development environment to try this. It's very simple to do. So just trying this in the browser, and then I will demonstrate how I have adopted this version for my own operating system, which gives interactivity to this original project, and hopefully this works becomes much more interesting now. So without further ado, let's actually start the demonstration. So here I want to download the code. I'm on Linux, but I'm not going to be using this fancy git clone things, just to make sure that anyone can easily follow this tutorial. So we just go into the downloads folder, right? So just want to extract here. All right, I don't need this anymore. And here we have the os.img file. So now we can load this file into the online emulator. So here I have the emulator copy.sh/v86. And here we want to load from the floppy drive, because bootOS defaults to floppy drive. So let's go to the downloads, and here os.img. Now, a few words on how this works, so you can know this from the README file. I've already kind of learned that. So it has, let me just get back here. So it has a source code. That gets written to the floppy image, and this is the source code that gets written to the floppy image. Then the assembler actually copies this to the memory, then assembles, and the assembled code, the machine codes, are written back to the binary file, to the same image, to exactly the same image, and then that file can be run under the bootOS. Okay, but in GameOS it's a bit different. So anyway, so here we boot successfully. So bootOS has the dir command to list all the files it has, and this 0 stands for source code, and this @ symbol stands for a binary executable. By default, so if I just type 0, nothing happens because it's not a valid, it's not an executable, it just hands. So this is okay. So reset. Then if I type @ symbol, it probably should hand as well. Yeah, and it does, because there is nothing there. It's just empty one. And what I need to do in order to make it run, I actually need to say 0ASM, which would, when I hit enter, what happens? So it reads the source code from this file and reads the output bytes to this file. So from now on, if I say @ I have the hello world, which comes from the assembled version of this source code. So this source code gets assembled by the assembler and gets stored to the floppy image. That's pretty much all about it. But you see, like, what's the downside of this? That if you want to change, if you want to assemble different code, you need to just drop back from this bootable environment back to your normal machine and just input the, just edit the text in the editor, for instance, and then you just need to like run this again. So it's a bit of a long process. So what I've done, so what I did, I actually I've adopted this 0ASM assembler to work under GameOS, which is my own operating system. Again, like as I've been mentioned before, like for running and developing, and now it's really cool. It would be really cool to develop boot sector games and apps using this assembler. So the next thing to consider, I'm gonna download my GameOS, so you can find this on my GitHub. The links would have been in the description below the video. So just go here and again, code, download zip, and go into downloads back. Okay, extract here, delete. So I have an entire series of live code in this GameOS, so for those interested, you may have a look. But what you need currently is this source GameOS dev pack and GameOS GameOS.img. So this is the file we're going to be running. All right, so here now just go back and choose the file. In this case, GameOS initially runs on the USB flash drive, so you need to use the hard disk image here in order to make sure that it works properly. Otherwise, it's just not going to be working. So downloads GameOS main source dev pack GameOS img and start emulation. Okay, so for those of you who have been following this series on GameOS, you probably remember that there were 5 user-defined programs. Now it's only 3 left because I've added the custom code editor to input the assembly code, and this ASM is the adopted version of 0ASM by Keyhan Vakil that now is available to work under the GameOS. Okay, so how this works? So first of all, the very first important thing to mention is that 0ASM does not support error handling in the way you might be used to that. So it either assembles the code or not assembles. And instead of reading the source code from the file, it reads from the buffer, which is in the memory where the code editor puts this to. I'll show you this in the source code at the end of this video. And then instead of writing this binary executable to the file, this assembled bytes, instead of writing this assembled bytes to the file, it just writes them to the scope of the hex editor in the GameOS. So if you're not familiar with the terms I'm currently talking about, you can just check the entire series on how I was building GameOS to get familiar with the environment. But anyway, the way how I made it possible to check whether the program actually has assembled or not is to have a look at the hex editor, and if there are some bytes, then most likely it has assembled properly. If not, then something has gone horribly wrong. And obviously, if it did manage to assemble partially the program, but failed to assemble the rest of that, then the output is not going to be valid. So that's another way how you can know that it's not working properly. But anyway, so let's get to the code editor. Well, let's start demonstration by the hex editor. So here we'll see the assembled bytes. Also, the last word stands. It's the relative offset of where the assembler is going to be putting the output byte. So currently, it's the little endian byte order for the hexadecimal number 0500, which is the address where it starts from by default. So from here, right? but it can be altered to start from whatever other place. I'll demonstrate you this just right in the moment. So here we go to the code, and let's try by a single instruction return, which is trivial, but just to give you an idea how it works. Now I always type new just to make sure that if there was some previously available bytes in the editor, just make sure to get rid of them, right? And then I say ASM, right? And then I go back to editor, and suddenly I have this C3, and C3 is the opcode for return instruction in x86 assembly. So we just successfully assembled a single instruction, which is really cool already, right? But now let's say we have not the one instruction, but many instructions, and we want to put them not at the very beginning, but let's say in this kind of like len number 2. So if I just alter this bit, so first I just erase what I have there, then going back to the editor, and then at address 06FE, for instance, I say 2005, which actually the actual address is 0520, but because of the little endian order of the x86 architecture, we need to make it like this. So this means, well, and by the way, the code is still in the buffer until I say code again and hit enter. It would be there, so I can still use ASM here, and going back to the editor and see like now C3 is available at the offset, at the user defined offset. However, it now overwrites this byte, but it's not really that kind of big deal. So we can say new, have a look at the editor again, and now we need to specify this byte again. So I can say 06FE 0005 and hit enter. And okay, did I do something wrong? Oh, I have free. No, not a free. I just wrong place. Sorry guys. So new, edit, and 06FE, right, and 0005. Yeah, so now I restore the byte. Okay, so if I assemble again and edit, now puts the code to the very initial position. So hope this is clear. Okay, now let's go to the code editor and try to code something a bit more decent. So I'm gonna be typing this. Well, actually, this here, this is the original. This is the original Hello World provided along with this Zero ASM project, but I'm going to be writing a little bit custom one, my own version. And another thing to consider, so despite the fact that compare command it seems like it's available there, and sometimes it works even, but in most cases, well, maybe I'm just doing something wrong, I know, but it doesn't really work that great for me. So instead of using the compare command to answer the question whether the value in the certain register is equal to 0 or not, I'm going to be using the AND command. So anyway, let's start with the hello world. So I can say move to SI and message. Message is going to be labeled. Please know that I'm not using the space here for otherwise it's not going to be working. So syntax should be mnemonics, then space, then first argument, comma, the second argument. This is very important if we have up to 3 arguments, okay? For otherwise it's not going to be working. Then I want to say move to AH. The constant value of, so we need the hexadecimal 0e to type to be able to type in the teletype mode. So this is the BIOS code to type in the teletype mode when it comes to print the character to the screen. However, another limitation, which is on the one hand it's cool, on the other hand it's a little bit not that handy really, that it doesn't use hex value. So we can say like this in this assembler. We can do we can say 0x0, we can say like this. So instead it uses octal numbers, and so we need to convert this hexadecimal number to octal, and in octal it's gonna be 16. So I'm currently not gonna be covering. So O stands for octal. So it's not the scope of this tutorial to show to teach you how to convert hexadecimal to binary and then back to octal and back and forth doing this. So it's really out of the scope. But anyway, just important thing to mention that we will need to only use octal constants, so not the hexadecimal but octal. So that's because of the tiny size of the assembler, so it's easier to parse octal numbers rather than the hexadecimal. So that's, I hope that is clear as well. Okay, So the next thing, we want to define the loop, and what are we going to be doing within the loop? So we want to load single byte. So SI is pointing to the message by typing load single byte. It just reads the value to AL and increments the SI pointer. Okay, then we want to print the character to the screen, so I can say int, and I can say here hexadecimal 10. Instead, I need to use the octal value, and it's gonna be 20. All right. Now the next thing, I want to figure out whether the AL register is equal to 0 or not. So I can simply say, simply end the AL register with its own self, and then I say jump 0. So if it is equal to 0 to the end, and n is another label, and otherwise I just want to jump to the loop. Okay, so now the next label is end, and here we just called int 0. I forgot. So the octal number, yeah, 40, just to return back from the app running. So 40 like this. And then the message, itself, here we define the bytes, and these bytes would represent the ASCII characters in octal codes. All right, so starting with H, and then I don't remember all of them by heart, but so 145, 145 defined by 0. 154 defined byte 0154, and for O 157 and defined by 0157. Now if I did type something wrong or did some sort of a mistake, then it's not going to get compiled, and the downside that I would be forced to write the code from scratch. However, if I succeed, then this sort of a thing should actually be assembled into the valid machine codes, which hopefully would result in printing the hello string without a new line. But anyway, so I just escaped from here. I say new to make sure that the buffer in the hex header has been cleaned up, and then I say ASM, hold my breath. I really hope that this did work, and now I'm going back to the editor, and it seems like it did assemble, well, at least something. So I can assume that most likely this is the valid machine codes to type hello. Okay, so but to make sure that this is so, I just first need to save this buffer as the prog1, so type 1 here, and if I just now run prog1, if I did everything properly, it now should print hello, which it does. Alright, so it wasn't really that trivial to get used to this sort of a thing, and I've spent around 5 hours to to complete a single hello world with this sort of an assembler. So it's really impractical. However, if the program fits in only 512 bytes, you don't really expect it to be practical. It's just a proof of concept and showcasing the great skills of the person who has created this. So Keyhan Vakil in this case. So thanks to him, because this is really cool what he did basically. Okay, so this is it regarding the demonstration, and now let's have a look at the source code. So I want to demonstrate the core parts of the original code, and then to emphasize what I've changed in order to adopt this for my operating system. And hopefully this is going to be useful for those of you who's playing around with this 16-bit real mode environment, if anyone is doing that actually. So yeah, I don't need this one. GameOS is still on the cards. I don't need this one. Yeah, so this is obviously the only source file, and this is called 0asm.asm. And here is the memory map of what it uses. So fixed subtable, symbol table, register table are the internal tables that it initializes in order to make the assembling work. Right, then these two are interesting. So this is where the input source code starts, and this is the address of where the output bytes occur when the assembly has been successful. But here is a first thing to mention. So because of the fact that bootOS, the minimalist operating system by Oscar Toledo, only can save the 512 bytes long files, This means that the source code, not the binary executable, that the source code for this assembly to fit into it would be limited to only 512 bytes, which in this case you won't be able to write a full boot sector program. So I've been counting, it's around all you can the rough estimate of the amount of bytes that you can write, assuming that you have only 512 bytes for source code, for assembly source code. It's around only no more than 100 bytes of executable. But if you want to have the 512 bytes executable at most, in that case you need kind of more memory, and that's the reason why in my adoption the size of the source code is limited to 2 and 4 kilobytes. So it's almost unlimited in terms of it should be fairly enough to type the entire 512 bytes executable. And this is the limitation because both bootOS and GameOS are not capable of running. Well, actually, potentially GameOS can run the bigger files, but anyway, that's the limitation for both systems. So just 512 bytes executable is the upmost limit. Okay, so where the source code locates and where the eventual binary machine codes gets where they land actually. Okay, so here after initializing the table, one most important thing, so we need to point SI to the input buffer to the source code literally, and DI point to the output buffer. And then when it comes to when the assembler has done its work, and when it comes to exiting from the process, right? It then does the following thing. So it just drops DI back to the where the output starts, and he stores that into the floppy image. And yeah, I also forgot to mention that in order to put the source code to the specific address, it loads, it reads the file from the floppy image and puts it there. So these are two essential places that I've changed in GameOS, and now let's have a look at how this works in GameOS. So we just go to source, GameOS dev pack, and it's called assembler.asm. Well, I could have called it 0asm, probably I should have, but just added the reference to the original project. I hope that's fairly enough. So here, well, first of all, yeah, another little thing to consider. So I just wanna share the updated memory map I have for this project. So let's duplicate this as well. So in order to be able to type the code dynamically, I've added a simple code editor which doesn't have that fancy editing features. It can't even navigate through the lines, only just type and erase within the single line. So if you did something wrong in above, you can't do anything there, you can jump there, and you can input the code only in one run. So if it doesn't work the next time, you need to do it from scratch. It's not the most handy thing ever, but that's the design decision that is forced by the environment all this stuff is working in. So anyway, I have, well, actually, I'm sorry guys, I saw 2 and 5. Yeah, actually I have not 24 kilobytes, but actually this is the number of bytes I have for a source buffer, so it's really more. Okay, and this is the address of where the source code is assumed to be, assumed to look up for a source code. So this is the address, so not oh my god, not here anymore, not at 6D, not at 6B00, but now it's available at 1A00, right? So what I did so far, so the very first change is here it is. So I'm no longer reading from the file, so instead I'm just pointing aside to where the source code is available. So All the things I've changed are now has this labeled commentary. So CMK stands for Keyhan Vakil. So all the changes made by me are available under the CMK label. So source ASM file on GameOS. So this is the address where the ASM source file created by the code editor under the GameOS is now available at, and output is still the same. And now in order to escape from this assembler, it just makes a far jump back to the GameOS shell. Okay, and here, instead of writing to a file, what it does, it looks up a byte, an offset byte in the hex editor that I've been demonstrating, where exactly he should place the code, so it's going to be available for GameOS, right? And then it just copies 512 bytes from the output and to the GameOS's hex editor. And that's pretty much all about it. That's kind of it. So, well, actually, yeah. So again, like, for those following the development progress of GameOS, I can just show you this tiny little code.asm. So this is a tiny little code editor that I've been demonstrating this already when I was typing in the assembly source code, right? So here it is. So nothing really special. It just writes to just initialize this segment pointing to the source, okay, both the data segment and the extra segment, and then just writes it there. Okay, that's pretty much all about it. And by the way, yeah, just to make sure that when I was debugging this, I saw that well, actually on Linux we don't store the carriage return byte, while here it wasn't initially stored. So I've altered this, so this code editor no longer stores the carriage return when the enter key has been pressed. But actually that doesn't really seem to be affecting much, because the problem I was just dropping the copying when encountering the 0 byte, but that was weird because the program itself might be containing 0 bytes in itself, obviously, and so I just need to alter this to make sure to copy the chunk of 512 bytes instead of dropping when it hits 0 bytes. So that's pretty much all about it. Okay, guys, so yeah, I think this is it regarding the demonstration and the explanations in regards to the source code. So many thanks to Keyhan Vakil for creating his absolutely amazing, outstanding, tremendous Zero ASM project, this x86 assembler. And for those interested to try this at home, you can just download the sources from GitHub and try this online emulator and play around with interactive assembling using GameOS by Keyhan Vakil and Zero ASM by Keyhan Vakil. Okay guys, this is it from my side, so thanks for watching. Until the next time, and take care.